Kick it. Let's go. All right. Physics. Week 8. Dynamics. Level up free body diagram and mechanics. Okay. We're going to take our time. Free body diagrams. Mechanics. Straight up. What's wrong with that word? Free body diagram. No? Mechanics? So basically, if you click free body here, your types of force, and you scroll, load more, scroll. This is the challenge. Let's get to it. You understand several kinds of forces, and we're going to make diagrams. We've already been doing diagrams with the drawings. I just call them drawings, but they are diagrams, and free body is just a mass being pulled on. Starting point, blah, blah, blah. Simple diagram shows an object here and interest and all the forces on it. It does not show the force that the object itself exerts on other objects. Just the force that are acting on the object itself. So it's all about this object and all the forces that apply on it. We're using force vectors, so the arrows that we're going to have are going to be force vectors. Normal force, weight. So the length of the arrows will mean something, right? Because that's the magnitude. And the direction, of course. You have to label the arrows that you draw. And we have a video here. We'll be all right. Let's move on. Example. This is the mass. We have the diagram here for the mass. We can expect what from this mass? We have a weight arrow, and we're going to have a tension arrow. The weight is here, pointing downwards. You'll notice that the next arrow will be the same length, because the magnitude is the same in opposite directions. No acceleration, that force is 0, therefore the rope exerts an upward force, and the FBD is complete. So there's no other forces on this. A free body diagram in systems. So we have two masses. So this is one diagram for the first mass, second diagram for the second mass. So mass 1, there's weight and tension. And they're equal. So we call it weight 1, tension 1. For mass 2, we have the tension that is caused by mass 1. And we also have weight on the mass 2. The weight of itself, pulling it down. Right? Like what are the forces on mass 2? Weight of mass 2, force by this mass on mass 2, and the tension upwards. I'm kind of surprised that T2 is the same length as like W2 and T3. But when we draw the diagram, we don't really know by heart the numbers that are going to be represented. So this is a fine diagram to begin with. And then as we calculate the force, we could make a better diagram at the end, which we will not do. I don't think so. Practice. Okay, so oops. So they wanted me to draw the puppy and the weight and the normal weight and the normal pushing back on it. A water balloon is falling from the second floor. So a water balloon would have a weight vector pointing down and nothing else because it's falling. Right, there's nothing pulling up. A curling stone is sliding along an horizontal ice surface. So sliding along the horizontal. Consider friction. So we would draw the weights, and there would only be a friction vector pulling backwards. Hold up. There's also the weight of the curling vector and the normal force from the ice on the curling stone. Okay, good. And these two would be equal, N and W. FF or FK, we've seen this before. And it's FF is general, but FK is more specific, the kinetic force. You see it pointing right, so that means the object would be moving left. Rightward force is applied to a bowling ball to roll it across the classroom at constant velocity. Consider friction. So now this one will have 4. We have the force applied and the friction. And because we are applying the force, we can expect this FF to be an FS, a static force. A pocket watch is suspended from a chain. Weight normal. Soccer ball has been kicked straight up into the air. Draw an FBD of the soccer ball when it's halfway back to the ground. So it's all the way up and it's falling down. So the only thing that would pull on it would be the weight. FBD of mass 2 is shown in the image. Okay, so mass 2 has its own weight, W, and a normal force from the table. It has also a force downwards, which we can call F1, created by mass 1. It is also to note that the normal force that we would draw would push back against both of these forces. So the N magnitude, because it's not moving up or down, the N magnitude, the length of it, would be the length of this plus this added together. If you add these two lengths, you make your N the same length. Now they're equal, and that's why this is not accelerating. A box is accelerated to the right when a rightward push is applied. Draw, and there is no friction. So we're just looking at one force. To the right, it's also a weight and a normal force. Yep. FA, yeah. Assume there's no friction. Draw an FBD of mass 1. So these are the things I want to take my time on a little more. Draw an FBD of mass 1. So mass 1, there's no friction. So mass 1 has weight and normal. Normal would be used for friction calculation. There's no friction. There's also tension in the cord here, which we can call, I wonder how they call it, T1 or T2, because it's called upon by mass 2. On mass 2, we have the weight and the tension. mass 1, mass 2. Should I just click the answers and explain them instead? Force is applied on the carton to move it at a constant velocity leftwards. There is friction, which is on the right, weight, and normal. Great. And yeah, we need all of this to calculate the final acceleration. Solving mechanics problem is the starting point for solving any problem that involves force. Let's write that here. They have rights reserved. Example 1. One mass on a rope problem. So a rope is holding up a 10 kilogram mass. What is the tension in the rope? Okay. Let's go. Because we have a number, then we can work. Example for the rope. We have a mass here, M equal 10 kilograms. There is weight, which I call Fg, and tension, T. Because I'm always going to start like this so you can better understand what's going on. So the sum of the masses in Y, which is equal to the tension plus the force of gravity. Both of these things are equal to ma, right? So basically this A means that the sum of the force will create an acceleration y, because it's a force y creates a y acceleration. And in our case, it's equal to 0, because A is equal to 0, because there is no acceleration. If that's the case, then this is equal to this, and the tension is equal to minus Fg. And Fg is mg. We're wondering what is Fg. We can say we know what Fg is. Fg is mg. So that's 10 kilograms multiplied by minus 9.81 meter per second square. T would be equal to minus. So minus here, minus there. We have a plus 98.1 Newton. It's a force. You can only sum forces. You can only sum forces together. Hi, Dwarf. Hello. I'm the teacher. We're doing physics. Okay, so chat is going to help us teach physics. That's why we're here. Draw an FBD. We got this. So there's multiple ways to write this, but this is basically what I wrote. I said the net force, which is this, the sum of the force, or F net, is going to be equal to T minus W. So in their case, they are saying that W is a positive force, and we are subtracting that. And I don't agree with that. I prefer writing the sum, as I'm writing it here. Sum them properly, which is 1 plus 2 plus 3 plus 4 plus 5. And then from inside there, right, know what is up and down. So the G here is down. This will make it so that our formulas make more sense. Sorry. We might run on some problem when it comes to testing and stuff. So F net is equal ma. That's the real, right? That's the real Newton law. The net force is equal to the acceleration on that mass. Yes. Next. So T minus W is 0, or T plus W is 0. They changed W for mg. Notice how g is not. Note the g is positive. Why? Because it's physics 11. Come on. 98. Yeah. So again, I'm gonna stick with my with our directions here. The negative sign of the downward acting weight came from a diagram. Negative sign of the downward acting. If we had used a negative value for g, we would have reversed this and ended up with the wrong answer. So remember, the signs are based on the FBD, and g is positive. No. Dynamics. Practice. One mass on a rope problem. So basically they're telling you to practice this. 45 kilogram metal bucket. Suspended from the ceiling. With a metal chain, what's the tension on the chain? The tension will be minus Fg. They want you to start from the top again. So when you do a problem like this, you start from the top, you draw your mass, you draw your two vectors, and then you sum up the forces in action. If it's equal to 0 because it doesn't move on that axis, which is the y-axis, if it doesn't move on the y-axis, then AY is 0 and it's equal to 0, and then you can form your statement and find the answer. So 45 times 9.5 will be about 450, 440. Elevator that weighs 3.5 is accelerated upwards. That's pretty good. I like this one. Practice 2. An elevator, which we can draw here. If you have a better drawing hand, then you can draw the elevator. And it weighs Fg. And I write my values here. So Fg is minus 3.5 times 10 to the 3 Newton. Is accelerated upwards. AY. So this is the real acceleration. So this elevator is going up. Whatever force is going on them, we have an AY of positive 2 meters per second square. What force does the cable exert to give it its acceleration? So we're asking the tension on the cable. So there's a tension, T. Fg, there's a mass. So we don't know the mass. I think we're going to have to find it out. So let's do Fnet. So Fnet. What's Fnet? So Fnet is the sum of the forces in Y, which is E plus Fg. And Fnet is equal to MA. Okay, buddy. MA. which is the acceleration on that mass. But this time it is not equal to 0, because that means there would be no acceleration. But there is a mass, and there is an AY, it's 2. And the mass is something like 100. It's never 0. So it's not going to be equal to 0, so we don't have that part. So if we go and replace things here, what do we want to know? T. So we can work with this part. T would be equal to MAY minus FG. We know what FG is. It's over here, 3.5. We can put that here, minus 3.5 times 10 to the 3. The issue that we have is that we don't know M, and we need to know M to work. And there's probably other ways to do this, but for now we can find M if we take Fg divided by gravity, right? Like basically this elevator has an Fg that is only due to its mass and gravity. So we can find M like this. Fg over G. So that's why I put the minus here, minus 3.5 times 10 to the 3. Divided by minus 9.81. So this is 3,500. I don't have a calculator yet. 3,500 divided by 9.81. 356.78. The 2 divided by minus 9.81. M is 356.78 kilograms. Now we can put that in the equation. Tension will be equal to mg. Is it minus mg? No. It's MAY minus FG. So M 356.78 times 2 meters per second positive. The mass is positive, the acceleration is positive. We're taking out of that the force. FG. Show me FG. I think I have an issue here. The FG was negative, wasn't it? So when I remove FG from my formula here, minus FG, it's going to be a minus from the formula and a minus from the FG itself right here. So this would be positive, right? Because it's minus here and then minus 3.5. That's the real value. So that's a plus. Put a star. And that makes more sense because the tension in the rope is fighting against Fg. So you have to include that. What is it? 3.5. 3.5 times 10 to the 3. Right, so the tension is going to be greater than this because the tension fights against Fg, and it also creates a work because it's better than Fg. So this times 2 equal 713. All of these numbers should be written down when you do math or physics, because then if there's a mistake or we're asking questions, you can come back to your calculations. 4,213.56 Newton. This is a vector, tension vector. Now, if you want to be sweet and put vectors everywhere, we're going to do that. So where does the vector go? This is a vector. Acceleration is a vector. Fg is a vector. It just looks nicer too. All right, so this is a vector. Vector. These are vectors, but I don't want to put them in the diagram. That's a vector. That's a vector. And M is not a vector. So is this the right answer? So first off, you can see that it's greater than Fg itself. If T would be equal to Fg, there would be no acceleration. Yet T is greater than Fg by a difference of 713. And that difference of 713 that is additional to this 3005 is the one causing this MAY, right? So basically the difference left is causing the acceleration. You divide it by the mass. Yep. 4,200. It's not a very precise answer. I don't see the reason why they put it in scientific notation like this if there's no precision here. Like, there's 13 newtons that are gone. If you do put precision like this, it's still scientific notation, but it's more precise. So, or if the elevator is accelerated downwards, right? So same thing is going to happen. We're going to end up with a tension that is smaller because the acceleration will be negative, which will reduce the 3005 to, 2000, 1000. And that's what the tension will be. The tension will be smaller than this. Should we do it? What do you think, Ice? Should we do it? That's just the answer. I don't think I want to do too many things. I want to hurry up a little more. 2 masses and 2 ropes problem. Yeah, let's get into the weird stuff. This problem is similar. In this case, there's 2 mass. Step 1. So we're going to work with 2 diagrams. So we're going to do this one also. Example, 2 masses. So this first mass has its weight, Fg, and a tension called T1, or tension on mass 1. And we have a square mass that is experiencing its own Fg, so we'll call it Fg2, just like weight 2. It has a tension 2, and it also has T1. Because this tension is the same as this tension, right? The tension in this cord, in this cord, caused by mass 1, right? Caused by M1, which is here, M1 and M2. So let's take a look at this diagram. So M2 has an FG2 force, but it also has a tension caused by something else. In this case, M1. So we're gonna have to figure out, I think, part of this first to know what T1 is, and then we'll have to bring that here to find what T2 is. We're doing two problems at once. All right. F net is going to be the sum of the forces, and it's going to be T1 for this one. T1 plus FG1. Why is there a 2 there? And for this one, F net will be T2 plus T1 plus FG2. So these are all the forces, and they're all equal to 0 because they're all canceling out each other. And reasoning is because there's no acceleration, right? They're not accelerating up or down by these forces. So from this idea, we get a statement that T1 is equal to minus FG1. Nice, because we know exactly what this is. And from this statement, from this idea, we get this statement. Oops. And we're going to find T2, I bet. So T2 will be equal to minus T1 minus FG2. And that's how we're going to find T1 and T2. We can't start here because we need T1. So we have to work with this first. Okay, so we get 1, 2. Up to now, I really hope that it's not too complicated. Up to now, doesn't seem too complex, right? The idea is that you draw your diagram, you recognize the forces in action, and then is it moving? If not, not that it's moving, but is it accelerating, right? Most of the time in these diagrams, including ropes and strings and etc., if it's moving, it's probably accelerating. But it's not moving, so it's not accelerating. So T1 minus mg, T1 will be equal to, this mass is 7 kilograms. I haven't written that anywhere, so this should be on your paper. Now, this really looks like physics. Congratulations. This is what you're here for. This is the real deal. So 7 times minus 9.81. Again, we did not put the minus here, so we have to put it here. Okay. T1 is equal to minus cancel out. 7 times 9.81 is 6867 Newton. Bring that over here to T2. So T2 is equal to minus 68.67 minus FG2, which is MG2 or M2G, right? So T2 is minus, and we can double check to make sure that our T is correct here. Is T a positive value, right? T is definitely a positive value. So we're good. So this is good. Now this T2 isn't going in the right direction, don't you think? This T2 has a minus here and a minus here. How in the heck is it going to end up positive? Let's figure out. Let's check it out. 68.67 minus, so M2, what's the mass again? 5 kilograms times minus 9.8. Oh, there's a little hope right here. Okay. Continue. 68.67 minus minus makes a plus. That's 49. So plus. I put a 1 again. I'll do it here. 5. 49.05. Huh. We get a T2 that would be minus. Hold up. Hold up. What's the issue? So if we end up with something minus here, that doesn't work out with our diagram. Let's go back to T1 for a minute. Now some of you have seen it already, but this T1 is a positive force because it's going up. This T1 is a negative force because it's pulling this mass down, right? And in this case, we should take note of that. So this is a plus. This is a positive force, but in this case, it's a negative force because it's pulled down. So this T1, in this case, should be negative, right? When you minus the T1, you minus the negative of this. This becomes positive. If you want me to do it like this, I sure can. And that's probably why they don't want us to get into that at your age. But who do you think you are? Minus 67, 68, 67. Right? This is T1, which is a negative force. So the formula says negative T1, which is true, and then the T1 itself is a negative force in this diagram. In fact, what we should be doing is respecting the fact that these are two, they might be the same problem, but they're two different situations. Right? They're two different systems. And if you would have drawn the system as like a problem by itself, you would have gotten a T1. I could have said that T1 is 68, and you would have said T1 is then minus 68 or so, right? And that's the step that we missed I missed, that is crucial. So making one mistake can cause these problems. So when I say you need to write things down, at least the essential, this is what for. We're trying to finish our problem, and it's giving us a minus t2. We have to go back. This is so normal. This is so normal in terms of physics. There's no way you can go through physics without going back to your ideas and finding it. Very normal. So this plus this is a t2, and that makes more sense now. T2 is a vector that whose magnitude, right? Its magnitude is going to be both of these vectors together, right? In order for this mass not to move, this vector, t1 and fg2, are completely counteracted by t2. So as you can see, a bigger vector. So let's add 68.87, 117.92. Whoa. Newton. It was still a pretty long problem. All right. Yep. So T1 is equal to mg1, and the minus here allows them to just have a positive T1. Sure. And then T2 is equal to T1 plus mg2, which is 118. So what they're saying is, they're just looking at magnitudes. This magnitude of T2 is equal to the magnitude of T1 and W2, and your F net would be T2 minus T1 minus W2. But every time you got to use 9.8 as your acceleration. And if you do that, you're kind of scrapping all the vectorial information from the plus minus that we've been working on for the past month, right? With kinematics. It's a matter of choice. If you want to do it, I'm cool. 2 mass, 2 ropes problem. Also, the reason why I expressed that this might be a better way to do it is because if you do some in university or some physics 12, we will go back to this basic idea, like we're not forgetting any information. Write your answer with your working learning guide and click on the links. Answer makes complete 2 blocks with mass 1 and 2 are hanging as shown. Case 1, the blocks are at rest. Find the tension on the rope T2. Okay. So T2 goes against FG. So T2 will be FG. T2 will be FG. This is FG, MG. FG is MG. The tension on T1. Okay, hold up. So they don't want us to use the... I like it. A challenge. Is this a challenge? So we start with M2. It has FG2 and tension 2. So T2 will be equal to minus mg. Whoa. We're skipping. We are skipping. F net is equal to T2 plus Fg2, which is equal to 0 because it's not moving. And so T2 is equal to minus Fg2. And T2 is equal to minus mg, or m2g, which is what we have. And g is the one that's minus, so that's why the minus and the minus cancel out. Okay. And for m1, we have t1, which should be a greater vector. F t1, we have t2 and fg2. My drawings are not really nice. Okay. So T1. So let's do Fnet. Fnet will be equal to T1 plus Fg2 plus T2, which will be equal to 0 because it's not moving. And so we take the statement, extract T1, yes. We have minus T2 minus Fg2. So what is T2 again? So T2, if we go back up, it's minus M2G. Oops. Hold up. I confused the numbers. Let's review the numbers. This is M1. So it has a T1 up like this. And it has a T2, but it also has an FG1. Right? It's caused by its own mass. Let's clutch this. 1, 1. So minus M2G minus M1G makes it so that you can put, so again, the minus I'm going to keep ahead because they don't like it. And if we do that and we put the minus outside, or even G outside, you'll get it. Then we have M2G plus M1G. I'll just put the minus outside because they don't like it. And I want to kind of follow that that idea. So T1 is minus. So what can we put? What can we group here? So basically G and G can kind of go outside of the bracket. And we're going to end up with G outside and M2 plus M1 inside. We could have wrote minus G like this. Remember, this G is also negative. And M1 and M2, if you add them up, you can add M2 to M1, or you can add M1 to M2, right? And you can see how, so we can reorganize this to make more sense. So the minus here is here because of my structure of the mechanic. M1 plus M2 can go before because we normally say mg, right? Times g. So the minus here is just here because of my structure, but you can see here how T1 is caused by summing up the masses. So what does this mean? This means that T1 does not care about a lot of things, right? So this T1 that's pulling the two masses together so this T1 that's pulling M1 and M2 is actually equal to summing them up together multiplied by G. So T1 is equal to Fg of M1 and M2. Right? Because this is Fg1 and this is Fg2. And if you sum them together, you get T1. Right? So it's basically saying T1 is minus Fg1 minus Fg2. Literally summing them up together. So in other words, T1 does not care about T2 in here. You see that on the right? T1 does not care about T2 at all. T1 can be found if you know the masses and the gravity, then you know what the tension one is. It's kind of like saying you only have one mass, like a total mass, and then T1 is fighting against that mass. I can simplify my point. M1 has an Fg1, M2 has an Fg2, and this is basically saying it's the same. It's saying it's the same as having one mass of M1 plus M2 and fighting against that as one mass instead of two mass. So this is what it's saying. Saying it's the same as that. Case 2. The blocks are accelerating upwards. Oh, by the way, because it's saying that, and we've only used those and no numbers, this means it's true for every scenario where you have multiple mass. And I bet it's true if you have more mass. We would have to do the math. The blocks are accelerating upwards with an acceleration. So again, rope with acceleration. I don't think I'm going to keep all the examples in the notebook, but see if I can reorganize them. So the tension in T2, so the blocks are accelerating upward due to the tension in the string. Okay. So this first mass M2 has an Fg2 and a tension 2. I don't think this tension is what they're referring to. So I'll say that F net, or you can write the sum of the force in Y is T2 plus Fg2, which is 0. Maybe not, because it's accelerating. MA2. Because it's accelerating, then one of these two has to be bigger. Because if they're equal, they're going to cancel out and this will be 0. But since this is accelerating, the acceleration is not 0, then if it's not 0, then T2 is probably bigger than FG2. I'll say plus plus. They want me to find T2, so that means only isolate T2. So MAY, which is not 0. The mass we don't have, and it's M2, by the way. M2AY. I'm not sure if I need to put an AY2 because it's on that mass, but we'll come back to that. I think it's going to be accelerating at the same rate. Minus FG2. T2 will be M2AY, or just A. FG2 will be M2G. And so we are looking at a factor here of M2. AY minus G. And this G is negative. I like to put this here just to remind ourselves why the minus is there as we explore this. Let's see what they think. So T2 is M2 times A plus G in this case, because the G is negative. Not negative for them. But my negative G here cancels out the negative there. So you get why I like to put this here. So basically this is saying that you'll take G, which is minus 9.8, and if it's just minus 9.8, there's no acceleration. If A is 0, right? So if A is 0, this goes away. You're left with M2 times G, which is minus Fg, which is true. T2 is equal to minus Fg when the acceleration is 0. If the acceleration is positive, all right, like plus, then if it's a positive acceleration, say plus 100, then this part is also a positive number because minus minus makes positive. So say anything like, it should be 9.81, right? Literally adding that up and then multiplying with the acceleration, the mass here. So this means that if you have a positive number here, okay, hold up, we can simplify this. Minus 9.8 is 9.8. So nothing's going to change. So if this is 0, then you have M2 times 9.8, which is the tension, which is a positive number because it's up. Sweet. If it's a positive number, like 2 or 3, then you're increasing that number. So you've increased your T, which maybe was 100 at first. Now because of this, it might be 130, which means you've increased the tension going up. So that's why you're accelerating up. And if that number happens to be a negative number, so it's accelerating downwards, think about it, right? If it's 0, there's forces but not accelerating. If it's minus 3, it means it's accelerating downwards. So this number is not what it used to be for the tension. There's a minus here, so maybe it's like 70. So that's what we've been seeing. If we lower the tension, we are actually letting it accelerate downward. Find the tension in T1. T1. What about T1? So this is M1, the second mass in the system, which is higher up. There's T2. And you'll notice I'm drawing over it. T2, because I can't stand bad diagrams. So T2 and what is it? FG2, right? That's it. So the sum of the forces in Y, which is F net, is equal to T1 plus T2 plus FG2. And it is accelerating, so it's equal to MAY. This is the statement which will take T1 is equal to MAY, so M1AY, or just A, because there's no AX here, there's just an AY, right? Minus T2 minus FG2 right? So we're just isolating T1 right here. Let's develop things that we know. So T2 is actually this mess. Not a mess yet. M2AY minus G. I did not practice this beforehand. I have fate, called fate. I'm also great with words. AY minus G minus FG2 is M2G. All right. What do you want me to do with this? Well, maybe we don't have anything to do with this, but is it true? Right? Is it true? Just look at this right here and tell me if that's true. Hey, let's go. So T1 is, first off, the acceleration. So this is the, okay, so I think we have to go back here. So is this true? T1 and T2 and FG2. Oh, hold up. Not FG2, again, it's FG1. Man, someone's gonna rage. Can't name names. FG1. Right, so FG1. Okay, let's fix that. Okay. T1, T2, and FG1. Got it. They make the mass accelerate in the y-axis. T1 is then this resulting, right? What is MAY? If you look at MAY here, what is that? That is the F net. That's F net. So the sum, or basically the rest, we could call it, not because it's at rest, but it's the rest, or the rest of, or the balancing act, right? And then we just want to double check T2 is M2, AY, and G. Nice. And FG1 is M1, G. Oh my goodness. So this is, so is this true? So the rest of it, this is going to be a positive number. If you take from the rest, anyway, that's too confusing. Let's continue the math. There's more to do. Oh yes, there's more to do. I notice that M1, let me take that off here. I notice that we have an M1 here and M1 here. So can we say M1 times AY minus G minus M2 AY minus G? Can we say that? He's like, what? So let's reorganize everything. M1 G AY, this first part, minus, I'm going to take that second part, M1G. Why are we doing this? This is so crazy. M2 AY minus G. It's fun though. I just noticed that these two M1s could be grouped together. Just the same way that we actually did that here. So if you see it here, you should probably do it. There's often a good reason. Like it ends up doing things for you. So this is true, right? I'm just getting that M1 out. Right? And then minus M2 AY minus G. I guess that's what Kara was doing in her class. So what now? Well, we have a common factor again. So common factor goes in front. We end up with M1 minus M2. Okay. Well, if you put the common factor in front, you would get AY minus G times what? What's left? M1 minus M2. And if you reorganize that to have M times G, like MG, like a FG, then you get M1 minus M2. I can't wait to see that answer and see if the minus that we work with changes this. Let's take a look. That's what I thought, yeah. There's a plus. I really feel that that is my mistake. This minus is my mistake somehow. It's somewhere in here. This first part is good, right? So this, and it's A plus G, which is what we have. It's like an A plus G. There's no reason why this minus is there. Like if because the G is minus and this is our decision, then the minus of the G and this minus cancel out. That makes a lot of sense. But you'll never have a minus mass to cancel out this minus in front. But that's why I'm saying this is different than this. That's why I feel that I've made a mistake, and I'll find it. Am I gonna have to speed up the video? This minus comes from where? Let's do it together. We don't do that often enough. So this minus comes with the minus m2, which comes from this. I'm so sorry, you can barely see that. No, my face is too important. Okay, let's continue. Oh, the minus here with the m2 comes with, or comes from this, which comes from this, right? Still a minus, which comes from this. And this comes from here. And again, that part inside is okay. It's clear because the g is minus. Right? And that minus comes from minus t2 again, which is causing the issues, is it not? Right. This T2 is a minus force. This T2 is a minus force. So when I develop it like so, this T2 is this T2 up here, and this T2 is this, right? It's a negative force. With the minus and everything. Like these are different T2s. And that is probably the sole reason why they choose to work with different minus and plus here. I don't think that's a good enough reason. I'm probably going to get bit hard for this. But I just don't think it's a good enough reason to change it. I think we should stick to the definition. So this T2 is a negative force. When we write plus T2, it's fine. Then we change it. It's a minus T2. That's fine. But we should remember that this is a minus force. And the minus here there is another minus here. Right? Should I put it in bracket? That's a good idea. A bracket minus. That's legit. So this minus comes from the fact that this T2 is a negative force. Okay, I think I'm going to review this, but let's go with this for now. So this is a plus because of this. They're all plus, which makes more sense, right? So this is the idea. It's minus T2, but T2 is actually minus T2 is actually minus M2 AY minus G. Yeah, I can see the level of complexity adding up for y'all. If we don't screw up somewhere, we're gonna screw up somewhere else. Like, if you ask me to say to do it without, so if you ask me to change this and put the minus where they belong, you're also asking me, or I would be asking you, to not do a G that is minus, to have a 9.8 without the minus. I just feel like this accommodation is not called for, because then we'll forget that the g is not a minus, and we will just forget where to put things, unless we just simply recognize that this T2 is a minus force, and it should be labeled as such, and maybe in this case, on the top part, T2 is a positive force, right? But in our case here, after the situation, because this is one situation, this is another situation. We have to respect that too. Let's continue and try to respect the situation. Okay. Elevator. Your knees buckle during the first seconds of going up in an elevator. Your body is responding to an increase in apparent weight. Everyone who is located on or near the surface has weight. Person stands on the scale. The reading on the scale is actually normal force. The situation becomes more complicated when the scale of the person experiences acceleration. Right, so you can imagine on a scale in an elevator, as you go up, your weight increases. Okay, you can check the videos if you want. Elevator problem. Jane weighs 600 Newton. What's her mass? Divide this by 9.8. You get 61 something. Jane places the scale on an elevator and stands on the scale. Assume that the bathroom scale measures normal force and not weight. Okay, so basically they're saying the weight is not going to be what's measured. The weight of Jane is 600. That doesn't change. That's her FG. Elevator scale problem. So Jane is in an elevator. She is this box. She has an FG, which is her weight, 600 Newton. But then what? There's a normal force, N. Right? And she's accelerating, right? Keep that in mind. What does the scale read if the elevator ascends at a constant speed of 5 ms? I feel like they're not giving everything, but the normal force would be closer to what Jane is seeing on her scale. And it has to do with the tension, T, which is greater than Fg, right? So T is greater than Fg, which causes the acceleration. In this case, are they saying that the tension is the normal force? We will assume so for now. So if it's going at a constant speed, there is no acceleration. The scale will read 600 Newton. There's no acceleration. It's literally like she's standing on it. Right? So N is equal to 600 also, which is a normal force. The force that's pushing against her feet, right? To keep her up. What does the scale read if the elevator ascends at a uniform acceleration? So A, acceleration equals 0. Oops. N equals 600 Newton. By the way, this Fg will be a minus 600 Newton. B. We have an acceleration of 3 meters per second square. Upwards. Ascend, yes, so positive. In this case, if we do the F net, or the sum of the forces in Y, by the way, this is more of a maybe a 12th grade language. So F net. So the net force is the normal force plus Fg. Right? The net force is the result. The result is m times 3. Okay. So the result is the acceleration. F net is equal, F is equal to ma. And the net force is those added together. So basically now we want to know what n is, because n is what's pushing against her. Normally it would be only Fg, but this part would be 0. In our case, this part is not 0. And following the math, we have a minus Fg. That's okay, because Fg is minus itself. It's down. So it's going to cancel out. That's why the normal force will be equal to mass times... Okay, so the mass, what's her mass? Found her mass earlier, 61.2. So we'll write m equals 61.2 kilograms. 61.2 times the acceleration of 3. Again, mass is positive, acceleration is positive, minus mg. G is the minus here. We never put the minus like this. This is my reminder for you. Okay. So n. So 3 times 61.2 is 183.6. The mass is 61.2. We could have done things differently. Huh? Times minus 9.81. N is, so 61.2 times 9.81. 600. 183.6. If you write well, you can read yourself well. Plus 183. We're good. We're good. So, do. And 783.97 Newton, because it's a force. And it's pretty natural because she's already fighting the elevator. Sorry, the elevator is the normal force pushing against her. The elevator is already fighting 600 Newton. But on top of that, it's got to fight the fact that it's accelerating her upwards. Or it's got to work towards accelerating her upwards. The difference is 184. And that 184 is the one causing the 61.2 mass to accelerate by 3 meters per second. Okay, so we can see here how this normal force is pulling. Normally, we would say the normal force is like just the floor reacting to you. In this case, it also refers to the tension. And it also refers to the scale, right? Scale itself is revealing this. What does the scale read if it descends? So we could, if you're good at it, if you notice that this is going to be the same equation, you can go ahead and write that down. Start from here, and is equal to MA minus FG, which will be 61.2 times minus 3 minus 61.2 times minus 9.81. So what are they trying to tell us? They want us to use the other formulas, I think. Which formula could we have used? M times A minus G. So we could have used this this formula here, right, to calculate the tension, which would be the same as the normal force. So we could have used this formula, yeah, because the normal force would be equal to the tension. Maybe it wasn't our place to take this formula and assume that the two masses are working together and assume that the tension is the normal force. But clearly, when we do the math, we will extrapolate that idea that we're using the same formula. This is M, A, and G from that formula. We could refer to it and say, well, hold up, let me just finish this. 61.2 times this is 600 something, and times 3, 637. Are you serious, Charles? It's a minus 0.37. Doing some tricks. Difference is 416. N is 416.77 Newton. This is what would be read. And it's lower than 600, which is normally her weight. Oh, I shouldn't be using this. I should be using 600 as the weight. Okay. Doesn't change anything. It's because the 8-1 probably. So this normal force is lower than it should be at 600. So clearly it let it happen if you want, and it doesn't go completely against the FG, or her force of gravity, which is the reason why it's accelerating downward. It's letting it accelerate. It's letting it have a net force that is less than 600. And the difference is about, what, minus 184 about. And this minus 184 Newton is the one causing the MA 61 times minus 3. If you're looking for A, 61 times minus 3 will give you back this. The point I want to make from earlier was that this line right here is MAY minus MG. And basically, if this is the same as this, and this formula MAY minus G is this. Oh, hold up. Where is it? Ah, there it is. MAY minus G. Then it means that T2, it's this one. T2 would be N, right? If MAY minus G is T, the tension in the chord or the resulting vector on the top, then this is the tension also, right? So it's not only the normal force, but it's also the tension. But we don't know, maybe there's not an actual string that pulls the elevator. Maybe the elevator itself has other mechanism that goes up, and then the normal force is pushing. Maybe it actually has, instead of a rope pulling the elevator, it's actually just a stick that's pushing the elevator up, and it's the same as a pull and a push is the same, and the tension would be the same as a push and a normal force. So you can see how it's all connected. And what was this equation for again? We came up with this equation because of this situation right here, when there's only a mass, no acceleration, and a tension, right? It doesn't matter if there's acceleration or not. So this here says that there is a tension, there's a Fg, and there can be an acceleration. Okay. Good. We'll probably have to use them again, so we'll come back to them. Guys, I think I'm gonna have to do 2 parts. This is getting pretty long. It's 10 o'clock. What does the scale read? Oh, we know that the scale reads that, yeah. Just where are we? We've done half? Okay. So that's gonna be it for that half, because the Atwood will take as much time. So this is good for this half. Yeah, forces in action. Yeah, cool. And this is the finding the net force. Sometimes the net force is found. We're actually finding one of the forces in the system that we're missing. That's mechanics right here. Let's take a break.